the electrician encountered a miswiring error. The grounded conductor of the 480/120 volts control transformer was incorrectly connected to the neutral busbar of the 277/480 volts lighting contactor. This neutral busbar should only be connected to the neutral derived from the lighting system. This created a voltage difference. The control transformer is designed to step down the 480 volts to 120 volts for the coil voltage of the lighting contactor. However, when the grounded conductor was incorrectly tied to the neutral busbar, the voltage on the 120 volts side of the transformer became 277 volts, which is the line to neutral voltage in a 277/480 volt system. This resulted in overvoltage on the coils. The 120 volts coils of the lighting contactor were designed to operate at 120 volts. Because of the miswiring, they were subjected to a much higher voltage of 277 volts. This overvoltage caused the coils to overheat and subsequently burn out. Finally, the burned out coils created a short circuit. This short circuit drew excessive current from the control transformer. This caused the transformer to overheat and fail, resulting in the flames witnessed. The severe damage and short circuit occurred because the miswiring created a direct path for the 277 volts voltage to flow through the 120 volts coils, causing them to overheat and fail. This is a dangerous situation that can lead to electrical fires and other hazards. To summarize, firstly, ensure that the grounded conductor of a control transformer is never connected to the neutral busbar of a lighting contactor or any other system with a different voltage. The neutral busbar should only be connected to the neutral derived from its own system. Secondly, always verify the voltage ratings of all components, especially coils, and ensure they are compatible with the voltage being supplied by the transformer. Using components with the wrong voltage ratings can lead to overheating, failure, and potential fire hazards. Thirdly, double-check all wiring connections before energizing any circuits. Careful inspection can help identify and correct miswiring errors before they cause damage or create hazardous conditions. Fourthly, use appropriate overcurrent protection devices, such as fuses or circuit breakers, to protect both the control transformer and the connected equipment from excessive current or due to short circuits or overloads. Ensure that these devices are properly sized to match the ratings of the equipment they are protecting. Fifthly, follow all applicable electrical codes and standards when installing and wiring control transformers and lighting contactors. These codes provide guidelines for safe wiring practices and help prevent common errors that can lead to electrical hazards. In more detail, consider the following. Control transformers are designed to provide a specific voltage output, typically lower than the input voltage, to power control circuits and devices. The primary function of a control transformer is to step down voltage, for example, from 480 volts to 120 volts or 24 volts to supply control power to components like relays, contactors, and solenoids. Control transformers are essential in industrial and commercial settings where different voltage levels are required for various control functions. The key components of a control transformer include the primary winding, which is connected to the higher voltage source, and the secondary winding, which provides the lower voltage output. The transformer core, typically made of laminated steel, facilitates the transfer of energy between the windings. Proper insulation between the windings and the core is crucial for safety and reliable operation. Control transformers come in various sizes and voltage ratings to suit different applications. They are selected based on the voltage requirements of the control circuits and the total volt amps load of the connected devices. It is important to choose a control transformer with adequate capacity to handle the load and to provide stable voltage output under varying conditions. Control transformers are installed in control panels, machinery, and other equipment where control power is needed. Proper mounting and wiring are essential to ensure safe and reliable operation. Control transformers should be installed in a well-ventilated area to prevent overheating. Wiring connections should be made according to the manufacturer's instructions and applicable electrical codes. Control transformers provide several benefits in electrical systems. They allow for the use of lower voltage control circuits, which enhances safety and reduces the risk of electrical shock. Control transformers also isolate control circuits from the main power supply, which helps to protect sensitive electronic components from voltage spikes and other disturbances. In addition, control transformers can improve the efficiency of electrical systems by reducing energy losses associated with long control wire runs. Common applications of control transformers include motor control circuits, lighting control systems, and power supplies for electronic devices. In motor control circuits, control transformers are used to provide the low voltage power needed for starting, stopping, and controlling motors. In lighting control systems, control transformers are used to power low voltage lighting fixtures and control devices. Control transformers are also used in power supplies for electronic devices to provide the required voltage and isolation. Regular maintenance of control transformers is essential to ensure reliable operation and to prevent failures. Maintenance tasks include inspecting wiring connections, checking for signs of overheating, and testing the voltage output. Control transformers should be kept clean and free of dust and debris to prevent insulation breakdown and overheating. Over time, the insulation in a control transformer can degrade due to heat, moisture, and other factors. Regular testing of the insulation resistance can help to identify potential problems before they lead to failures. Control transformers should be replaced if they show signs of damage, such as cracked insulation, loose connections, or abnormal voltage output. Troubleshooting control transformers involves checking the input and output voltages, inspecting wiring connections, and testing the transformer windings for continuity and shorts. If the transformer is not providing the correct voltage output, the problem may be due to a faulty transformer, a wiring issue, or an overload in the circuit. Control transformers can be protected from overloads and short circuits by using fuses or circuit breakers. These devices should be sized appropriately to match the transformer's voltage and current ratings. Overcurrent protection devices can prevent damage to the transformer and connected equipment in the event of a fault. It is important to understand the voltage and current ratings of control transformers to ensure proper selection and operation. The voltage rating indicates the input and output voltages of the transformer. The current rating indicates the maximum current that the transformer can safely supply. Exceeding the voltage or current rating of a control transformer can lead to overheating, damage, and potential fire hazards. Electrical codes and standards provide guidelines for the installation, wiring, and protection of control transformers. These codes and standards are developed to ensure the safety of electrical systems and to prevent electrical hazards. It is important to follow all applicable codes and standards when working with control transformers. Safety precautions should be taken when working with control transformers to prevent electrical shock and other hazards. Always disconnect power to the transformer before performing any maintenance or repairs. Use insulated tools and wear appropriate personal protective equipment, such as gloves and safety glasses. Never work on live electrical circuits unless you are qualified and authorized to do so. Understanding the function, operation, and maintenance of control transformers is essential for electricians, technicians, and engineers who work with electrical systems. Proper selection, installation, and maintenance of control transformers can help to ensure the safety, reliability, and efficiency of electrical equipment and systems. In addition to the points already discussed, let's delve into more technical aspects of control transformers and related safety measures. The impedance of a control transformer plays a crucial role in limiting fault currents during short circuits. Transformer impedance is the opposition to the flow of alternating current and is typically expressed as a percentage of the transformer's rated voltamps. A higher impedance transformer will limit fault currents more effectively, reducing the risk of damage to equipment and minimizing the potential for electrical hazards. When selecting a control transformer, it's important to consider the inrush current characteristics of the connected loads. Inrush current is the high initial current drawn by inductive loads such as motors and transformers when they are first energized. Control transformers must be able to withstand the inrush current without experiencing voltage drops or overheating. Some control transformers are designed with special features, such as inrush current limiting devices, to mitigate the effects of inrush current. The use of properly sized conductors is essential for ensuring the safe and efficient operation of control transformers. Conductors must be sized to carry the full load current of the transformer, as well as any potential overload currents. The National Electrical Code, or NEC, provides guidelines for conductor sizing based on ampacity, which is the current carrying capacity of a conductor. The NEC also specifies requirements for conductor insulation and protection. Grounding of control transformers is critical for safety and for preventing electrical shock hazards. The grounding system provides a low impedance path for fault currents to return to the source, which helps to trip over current protection devices and energize the circuit. The NEC specifies requirements for grounding control transformers, including the size and type of grounding conductors. Bonding is the process of connecting metallic parts of electrical equipment together to create a low impedance path for fault currents. Bonding helps to equalize voltage potentials and to minimize the risk of electrical shock. The NEC requires bonding of control transformer enclosures and other metallic parts to the grounding system. Overcurrent protection devices, such as fuses and circuit breakers, are essential for protecting control transformers from overloads and short circuits. These devices are designed to interrupt the flow of current when it exceeds a predetermined level. The NEC specifies requirements for overcurrent protection of control transformers, including the size and type of overcurrent protection devices. Surge protection devices, also known as transient voltage surge suppressors, are used to protect control transformers from voltage spikes and surges caused by lightning, switching transients, and other disturbances. Surge protection devices divert surge currents away from the transformer and to ground, preventing damage to the transformer windings. The location of a control transformer can affect its performance and reliability. Control transformers should be installed in a well-ventilated area to prevent overheating. They should also be protected from moisture, dust, and other contaminants. Control transformers should be mounted securely to prevent vibration and movement. The environment in which a control transformer operates can affect its lifespan. High temperatures, humidity, and corrosive atmospheres can accelerate the degradation of transformer insulation and other components. Control transformers should be inspected regularly for signs of damage or deterioration. Testing of control transformers can help to identify potential problems before they lead to failures. Common tests include insulation resistance tests, turns ratio tests, and voltage regulation tests. The results of these tests can be compared to the manufacturer's specifications to determine if the transformer is operating properly. Documentation of control transformer installations and maintenance activities is important for tracking transformer performance and for ensuring compliance with electrical codes and standards. Documentation should include transformer specifications, wiring diagrams, test results, and maintenance records. Training of personnel who work with control transformers is essential for ensuring safe and reliable operation. Training should cover transformer principles, installation procedures, maintenance practices, and troubleshooting techniques. Proper disposal of control transformers is important for protecting the environment. Control transformers contain materials that can be harmful to the environment if they are not disposed of properly. Control transformers should be disposed of in accordance with applicable environmental regulations. Energy efficiency is an important consideration when selecting and operating control transformers. Energy-efficient transformers can reduce energy consumption and lower operating costs. Energy-efficient transformers are designed with low loss cores and windings, which minimize energy losses due to heat and magnetic hysteresis. The load on a control transformer can affect its efficiency and lifespan. Control transformers should be operated at or near their rated load to maximize efficiency and to prevent overheating. Overloading a control transformer can lead to premature failure. The power factor of the connected loads can affect the performance of a control transformer. Low power factor loads can increase the current draw on the transformer and reduce its efficiency. Power factor correction capacitors can be used to improve the power factor of the loads and to reduce the current draw on the transformer. Harmonics are distortions in the alternating current waveform that can be caused by nonlinear loads such as electronic devices and variable frequency drives. Harmonics can increase the current draw on control transformers and cause them to overheat. Harmonic filters can be used to reduce the levels of harmonics in the electrical system. Redundancy can improve the reliability of control transformer systems. Redundant transformers can be installed in parallel to provide backup power in the event of a transformer failure. Redundant transformers can also be used to increase the capacity of the system. Remote monitoring of control transformers can provide valuable information about their performance and condition. Remote monitoring systems can track transformer voltage, current, temperature, and other parameters. This information can be used to identify potential problems and to schedule maintenance activities. Artificial intelligence and machine learning are being used to improve the performance and reliability of control transformer systems. These technologies can be used to analyze transformer data, predict failures, and optimize transformer operation. Ongoing research and development efforts are focused on improving the design, materials, and manufacturing processes of control transformers. These efforts are aimed at increasing transformer efficiency, reducing transformer size and weight, and improving transformer reliability. Standards organizations such as the Institute of Electrical and Electronics Engineers, or IEE, and the National Electrical Manufacturers Association, or NEMA, develop standards for control transformers. These standards cover transformer performance, safety, and testing requirements. Compliance with these standards is important for ensuring the quality and reliability of control transformers. Control power transformers, or CPTs, are a type of control transformer specifically designed for use in industrial control circuits. CPT are typically smaller and more rugged than general-purpose control transformers. CPT are designed to withstand the harsh environments found in industrial settings. Buck-boost transformers are a type of control transformer that can be used to raise or lower voltage by a small amount. Buck-boost transformers are often used to correct voltage sags or swells in electrical systems. Autotransformers are a type of control transformer that uses a single winding for both the primary and secondary circuits. Autotransformers are smaller and more efficient than traditional two-winding transformers. Isolation transformers are a type of control transformer that provides electrical isolation between the primary and secondary circuits. Isolation transformers are used to protect sensitive electronic equipment from voltage spikes and other disturbances. Constant voltage transformers, or CVTs, are a type of control transformer that provides a stable output voltage even when the input voltage varies. CVT are often used to power critical loads that require a stable voltage supply. Dry-type transformers are a type of control transformer that uses air as the cooling medium. Dry-type transformers are typically used in indoor applications. Liquid-filled transformers are a type of control transformer that uses oil or other liquid as the cooling medium. Liquid-filled transformers are typically used in outdoor applications or in applications where high power levels are required. Submersible transformers are a type of control transformer that is designed to be submerged in water. Submersible transformers are used in applications such as underground vaults and underwater equipment. Encapsulated transformers are a type of control transformer that is encased in a resin or other material. Encapsulated transformers are used in applications where protection from moisture and other contaminants is required. High-frequency transformers are a type of control transformer that is designed to operate at high frequencies. High-frequency transformers are used in applications such as switching power supplies and electronic ballasts. Pulse transformers are a type of control transformer that is designed to transmit short pulses of energy. Pulse transformers are used in applications such as radar systems and medical equipment. Current transformers, or CTs, are a type of control transformer that is used to measure alternating current. CT are used in applications such as power metering and protective relaying. Potential transformers, or PTs, are a type of control transformer that is used to measure alternating voltage. PT are used in applications such as power metering and protective relaying. Instrument transformers are a general term for CT and PT. Instrument transformers are used to provide a scaled-down representation of current or voltage for measurement and protection purposes. Three-phase transformers are a type of control transformer that is used to transform three-phase power. Three-phase transformers are used in applications such as power distribution and motor control. Single-phase transformers are a type of control transformer that is used to transform single-phase power. Single-phase transformers are used in applications such as lighting and small appliances. Multi-tap transformers are a type of control transformer that has multiple taps on the primary or secondary winding. Multi-tap transformers allow for adjusting the output voltage to compensate for voltage variations. Variable transformers are a type of control transformer that allows for continuously adjusting the output voltage. Variable transformers are used in applications such as testing and calibration. Phase-shifting transformers are a type of control transformer that is used to shift the phase angle of the voltage or current. Phase-shifting transformers are used in applications such as power system stability control. Rectifier transformers are a type of control transformer that is used to provide alternating current power to rectifiers. Rectifier transformers are used in applications such as DC power supplies and battery chargers. Inverter transformers are a type of control transformer that is used to provide alternating current power from inverters. Inverter transformers are used in applications such as uninterruptible power supplies and solar power systems. Welding transformers are a type of control transformer that is used to provide power for welding. Welding transformers are designed to provide high current at low voltage. Mining transformers are a type of control transformer that is used in mining applications. Mining transformers are designed to be rugged and reliable in harsh environments. Traction transformers are a type of control transformer that is used in electric locomotives and other traction equipment. Traction transformers are designed to be lightweight and compact. Distribution transformers are a type of control transformer that is used to distribute power to homes and businesses. Distribution transformers are typically mounted on poles or pads. Substation transformers are a type of control transformer that is used in electrical substations. Substation transformers are designed to handle high power levels. Generator step-up transformers are a type of control transformer that is used to increase the voltage from generators to transmission voltage levels. Generator step-up transformers are typically very large and powerful. Transmission transformers are a type of control transformer that is used to transmit power over long distances. Transmission transformers are designed to operate at very high voltages. The connections, delta and Y, describe how the three phases of a three-phase transformer are interconnected. A delta connection is a closed-loop configuration, while a Y connection has a common neutral point. The choice of connection affects the voltage and current characteristics of the transformer. The turns ratio of a transformer is the ratio of the number of turns in the primary winding to the number of turns in the secondary winding. The turns ratio determines the voltage transformation ratio of the transformer. The volt-amps rating of a transformer is the product of the voltage and current ratings. The volt-amps rating indicates the apparent power that the transformer can deliver. The impedance of a transformer is the opposition to the flow of alternating current. The impedance is typically expressed as a percentage of the transformer's rated volt-amps. The efficiency of a transformer is the ratio of the output power to the input power. The efficiency is typically expressed as a percentage. The regulation of a transformer is the change in output voltage from no load to full load. The regulation is typically expressed as a percentage. The insulation class of a transformer indicates the maximum operating temperature of the transformer insulation. The insulation class is typically expressed as a letter such as A, B, F, or H. The cooling method of a transformer indicates how the transformer is cooled. Common cooling methods include air natural, air forced, oil natural, and oil forced. The enclosure type of a transformer indicates the degree of protection provided by the transformer enclosure. Common enclosure types include NEMA 1, NEMA 3R, and NEMA 4. The standards compliance of a transformer indicates the standards that the transformer meets. Common standards include ANSI, IEEE, and NEMA. The manufacturer's warranty of a transformer provides protection against defects in materials and workmanship. The manufacturer service support provides assistance with installation, maintenance, and troubleshooting. The price of a transformer depends on its size, features, and manufacturer. The lead time for a transformer is the time required to manufacture and deliver the transformer. The availability of a transformer depends on its size, features, and manufacturer. The application of a transformer determines the type of transformer that is needed. The operating conditions of a transformer affect its performance and lifespan. The maintenance requirements of a transformer should be considered when selecting a transformer. The life cycle cost of a transformer includes the initial cost, operating costs, and maintenance costs. The return on investment of a transformer should be considered when selecting a transformer. The environmental impact of a transformer should be considered when selecting a transformer. The safety aspects of a transformer should be considered when selecting a transformer. The reliability of a transformer should be considered when selecting a transformer.